Hello, this is a lecture that's an introduction to waves, and I'll be mainly talking about vocabulary words, but also some of the workings of physical phenomena in this lecture so that we can all be on the same page when we start talking about why certain things happen in waves when we meet next. All right, so as a warm-up, what I'd like you to do is to consider this mass that is mounted on that spring in such a way as it can oscillate back and forth as we saw in our simple harmonic motion unit. And what I'd like you to do is graph the position of the block as a function of time after it gets released. I'd also like you to consider this situation, which I'll animate a little bit with my mouse. What I have here is a rubber ducky that is on top of a water wave. And as we know water waves do, this water wave is moving. It's not just a stationary wave. It travels, and it's traveling to the right. And what I'm trying to show here is that the rubber ducky bobs up and down, but the rubber ducky does not surf the wave. It doesn't change its horizontal position. As the wave moves under the duck, the wave is propagating slowly to the right like that. But then each time the wave shifts under the duck shifts down to be on top of the height of the water at that particular horizontal location. So I'm imagining that this water wave has a certain velocity to the right, and this ducky is just floating on the top of it. And I'd like to emphasize, this is a camera shot. This is like something I would use a camera to do. And I'd like you to consider, what are the axes of this camera shot? It might be kind of a stretch. But what are the axes? And then I'd also like you to draw a separate graph, the vertical position of the rubber duck as a function of time. I request that you pause the video to do this. I think that it will help you understand it better if you pause and try and understand these and produce these graphs before you go on and watch the explanation in the next slide. All right, here I go on to the next slide. All right, so I hope you had something like this. If it was shifted down, if it went into negative territory, then that's okay. But it's an up and down graph. And one thing I want to draw attention to is the fact that this is position on a vertical axis as a function of time on a horizontal axis. Okay, with the rubber duck, I want to suggest that a camera image, when you consider what is being communicated about the height of this wave, it is vertical position as a function of horizontal position. A vertical position of the wave in meters as a function of how far the point you're considering is from the left part of the camera image. What is the height of the wave at this horizontal position? Well, there it is. What's the height of the wave at this horizontal position? Well, there it is. This camera image is like vertical position as a function of horizontal position, with both axes having units of meters. That is to be contrast with the duck's position as a function of time. The duck, like the mass on the spring, sort of bobs up and down with position on the vertical axis and time on the horizontal axis. Why am I doing this? These graphs are not waves. These graphs of something as a function of time, you might call them a wave in math class. But in physics class, we'll only use the word wave to describe something that has spatial extent. These oscillating position as a function of time functions are not themselves waves. The thing that is described with this vertical position as a function of horizontal position, this thing that is moving to the right under the rubber duck, that is a wave. And what's the difference between that thing and this thing? Well, this is more of a graph of something evolving in times, and this is an entity that has sort of a spatial extent. Okay, so I'm still sort of working on what the question of what a wave is. In the last class, I gave an example of something that a wave is not. I'll say a little bit more in this slide about what a wave is, and I'll also talk a little bit about a related word, vibration. There are a number of different acceptable answers to the question, what is a wave? We're not going to name a bunch of types of waves in this slide. Maybe we'll talk about that in class. A few fine answers to the question of what is a wave is that a wave involves a transfer of energy and momentum from one location to another without transporting matter from one location to another. You can imagine that if I tossed a ball across the physics lab to you, and you caught it on the other end of the physics lab, I would have sort of transferred some energy and some momentum through the ball to you, into your hand. But I would have had to transport the ball, the mass of the ball, in order to achieve that. If, however, you and I stood across the physics lab, each holding a slinky, and I jiggled the slinky up and down, it would send a wave along the length of the slinky, and that disturbance, that energy, that momentum would travel from my hand to your hand, but I wouldn't have thrown you a slinky. I wouldn't have transferred bulk mass from my hand to yours. And so that's why one key feature, a defining feature of a wave, is that it involves a transfer of energy and momentum without a bulk transfer of matter. Another thing that we say about waves is that it is a disturbance that travels through a medium. What is a medium? It's something through which a wave travels. What is the medium that I just described in my example of jiggling a slinky and the disturbance travels to you? The slinky is the medium. Right now, I am talking and the sound of my voice is propagating through the medium of the air in waves of sound. If there's an earthquake, the ground is the medium through which the shock waves travel. Water is a medium for the travel of water waves. A medium is a vocabulary word that we'll need to be able to use, and the medium is that through which the wave travels. If I jiggle a slinky and it travels to you, what is the wave? Is it the moving of the slinky, or is the movement of the slinky just a symptom of a wave that's on the slinky? This is a fine distinction. My main advice is don't worry about it. But if you refer to the motion itself of a wave as a wave, then you're going to be okay. Vibration is a word that is kind of similar in that it can be used to refer to the motion of the disturbance. You can use the word wave or vibration for the motion of the disturbance. More often we say a vibration is the cause of a disturbance. When I was giving that example of me jiggling a slinky and you holding the other end of the slinky, my jiggling I will call a vibration. Like my vibration, my jiggling of the slinky caused the wave to propagate down the string. And again, in physics class, a wave is something that has spatial extent. So a sinusoidal function of time is not an example of a wave. The way that employment goes through cycles is not an example of a wave to us. Okay. Here are some more vocabulary words about waves. You can see how, I guess, an up and down jiggling of the slinky will create a certain type of disturbance. And it's sort of a different picture. It's a different sort of camera image compared to what would happen if you held one end of a slinky and I held the other end. I made a vibration that went in and out along the direction of the slinky. Can you imagine how that disturbance would propagate? I'll certainly show you in class. I'll also show you with a little bit of a YouTube video in a second. This type of disturbance would create something like this, regions where bits of the slinky were close together and regions where bits of the slinky were far apart. That is the same sort of thing that happens in air. When you speak, bits of air are compressed together and bits of air are stretched a little farther apart. And so this up and down type of wave is different from the type of wave captured in this in and out slinky wave, which is also a similar type of wave to what's going on in the air here. I'm going to introduce the vocabulary words that differentiate those in a second. But first, I'm going to play this video. If you can't see it on this screencasting very well, you might view it yourself. I'm here at 45 seconds in.
Looks like this. We have a bunch of oscillators, maybe represented by these little cubes, and they have an amplitude of oscillation that's up and down.
Okay, so what is up and down? The actual motion of the bits of this medium is up and down, and the direction of propagation of the wave is along sort of diagonally down and to the right here. And so you see how the actual bits of medium are moving up and down, but that is not the same direction as the travel of the wave. That typifies what's called a transverse wave. In this picture here, bits of slinky travel up and down, but the wave itself travels to the right. In other words, the particles in the medium are traveling perpendicular to the direction of the wave's propagation. I'll draw on here the direction of the wave's propagation. Examples of transverse waves include water waves. If you pluck a string on a musical instrument, or it turns out light waves are actually transverse waves. They don't have a medium. They're oscillations of electric and magnetic fields. You don't need to know that, but these are all examples of transverse waves. And again, let's look down at this picture. This disturbance travels to the right again. But here, the actual bits of slinky move right and left. Let me make that a little bit more dramatic with this video. Same video, actually fast forwarded to 2 minutes and 15 seconds. Look at the bits of this medium.
The second kind of wave is called a longitudinal wave. It's as if you had this...
Do you see that? If you don't see it very well on the screencast, go visit it yourself. The actual bits of the medium travel left and right, and the wave itself travels to the right. So the motion of the bits of the medium is in the same direction as the propagation of the wave. That typifies a longitudinal or compression wave. Particles in the medium travel in the same direction as the wave propagates. Earthquakes in the ground work like that. Sound in the air works like that. Transverse waves versus longitudinal waves. I'm going to make another observation and a vocabulary word based on that. Some waves clearly travel. In the first example, this water wave traveled to the right and the rubber duck was bobbing up and down on it. Some waves, it's not easy to say that it travels. Those are called standing waves. Check out this video, either on the screencast or by going to YouTube yourself.
I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point.
You don't need to worry about that. We will talk about that later. All I want you to see from this video is that if you just saw the video of that wave, it would be hard for you to say which way it was traveling, because each individual particle just moved up and down, and every particle moved up and down at every moment. It would be hard to say, oh yeah, that is moving to the right, because to me it just looks like one stationary thing that's oscillating. A standing wave is a wave that doesn't clearly travel in one direction or more. This is the video that we went to, and I'll show you, we'll talk more about standing waves in the classes to come. All right, I'm going to talk about some more vocabulary words, and in particular look at the anatomy of a transverse wave and talk about some words we use with transverse waves. Transverse waves, remember, are where the particles in the medium move perpendicular to the direction of the wave's travel. A high point is known as a peak. A bottom point is called a trough. The distance from peak to peak, which is also the distance from trough to trough, is called the wavelength. And I'd like to talk about wavelengths for just a second. This looks a lot like some things you see in math class that are functions of time. But remember, we're talking about something that has a spatial extent, like a water wave. This is a graph of vertical position as a function of horizontal position. This is like a camera image. The units of wavelength from peak to peak are meters. It's not like period, seconds, although we will talk about the period of a wave. We have the speed of propagation, the distance from the midline, this is called the midline, to the peak is called the amplitude. The amplitude is not the distance from trough to peak. The amplitude is from the midline to the peak. All right, both axes are positions and have units of meters. However, if this wave also travels, let me show you a video actually that shows that wave traveling. There it is. There it's traveling. See how it sort of evolves in space and time? You can imagine that if I were camped out at a particular location, say right here where those light graph lines intersect, I could ask the question, boom, there's a peak. How long to the next peak? Boom. How long to the next peak? Boom. How long in seconds between the time the peaks passed me? The answer is the period of the wave. The period of the wave is the time, measured in seconds, for a full cycle of the wave to travel past a particular point. So let's measure that again. I'm going to camp out right there and ask, what's the period? 1, 1,000, 2, 1,000, boom. 1, 1,000, 2, 1,000. Nope, oh no, went on to the next one. Too fast. My point is that you can ask the time for successive peaks to pass by a certain location. That amount of seconds is the period of the wave. The inverse of the period of the wave is known as the frequency of the wave. We've met frequency before. It's 1 divided by the period. It's measured in cycles per second. Mathematically, that's the same as 1 per second because a cycle is mathematically 1. And a synonym for that unit is hertz, which we abbreviate capital HZ. Okay, so let's look at that one more time at this video. The period, the time for successive peaks to cross is now to now. And so I counted about 2 seconds there. The period was about 2 seconds, and so what does that make the frequency? About 0.5 hertz. 1 over 2 seconds is 1/2 hertz, or 0.5 hertz. You're responsible for knowing all the words that were introduced on this page. This page contains only, I believe, a couple of new words. This is about the anatomy of a longitudinal wave. I'll do wave anatomy 2 there. A longitudinal wave has regions where the bits of the medium are extra close together and regions where the bits of the medium are extra far apart. There's a wavelength, which is, again, the distance in meters between successive, or I guess between repetitions of the wave. The regions where everything is pressed close together is regions of compression. The opposite of compression, the regions where the bits of the medium are spread farther apart, are called rarefaction. You might have heard of rarefied air at high elevations. That means that the air is spread farther apart, and one consequence to being in a region of rarefied air is that it's harder to breathe. You get less oxygen. Period and frequency are defined the same as before. That is, the time for successive peaks of compression to pass. So let's do an example with that wave. It's this one here. So I've got this slinky and there's that hand there. Let's measure how long between successive regions of compression cross the location where I put my mouse. I'm going to put my mouse right here and measure now. Go. 1, 1,000, 2, 1,000, 3, 1,000. Let's try that again. 1, 1,000, 2, 1,000, 3, 1,000, boom. I measure about 3 seconds as the period there. I could have chosen any location along the slinky to measure the time between periods of successive compression, but I get about 3 seconds there. And so what does that make the frequency? About 1/3 hertz, 0.33 hertz. How many complete cycles pass by my mouse cursor per second? 1/3 of a complete cycle, not a whole complete cycle. All right, the last thing that I want to talk about is the relationship between the velocity of a wave's travel, the frequency it has, and its wavelength. And I'm going to do this derivation a little bit hand-wavy-like, but we know that velocity of an object is the distance that it travels divided by the time it takes to travel that distance. Well, if you consider that a wave is traveling, and you plant your mouse cursor somewhere, you might consider how much of the wave has gone by you during a travel time of one period. Well, I guess one complete wavelength of the wave goes by you during each period. So we can sort of be like, oh, the velocity of the wave, the distance traveled, is lambda, the wavelength in meters, divided by t, the period in seconds. V equals lambda f, where f is the frequency there. Because you see, the frequency is the inverse of the period. Alrighty, so let's do a quick example of this. The velocity of sound, at sea level at least, is about 340 meters per second. What is the wavelength of a pure 440 hertz tone? I wonder if I can pull up a 440 hertz tone for you. Let me do a brief little search here off my computer. 440 hertz. That is a 440 hertz tone, apparently on a YouTube video that lasts 2 hours. That's useful for you to tune your instrument to. But I wonder, as different successive peaks of compression and rarefaction dumped into my ear as I was listening to that, how far apart were the successive peaks of compression? How far apart were the successive areas of rarefaction? Well, you can see that, I guess, the velocity of the wave is the wavelength times the frequency. So the wavelength is the velocity divided by the frequency. It's given that just sound being what it is, the velocity of all sound around sea level is about 340 meters each second. That divided by 440 hertz. A hertz is 1 per second, so those seconds in the denominator of both the numerator and the denominator cancels, leaving something with units of meters. That's good because I want the wavelength, and the wavelength is about 0.77 meters, about 77 centimeters of wavelength for this A440 hertz note.